Let's start with the numbers, because without them, the paradox doesn't quite land the way it should. The Milky Way galaxy contains somewhere between 200 and 400 billion stars. That number is genuinely difficult to hold in your head. If you tried to count them at 1 per second, you'd need over 6,000 years just to finish counting. And that's our galaxy alone. The observable universe contains somewhere around 2 trillion galaxies, each with their own hundreds of billions of stars. We're talking about a number so vast that our brains aren't really equipped to process it honestly. We just read the figure, nod, and move on. But try not to do that here, because the scale is the whole point. Now here's where it starts to get uncomfortable. Astronomers have confirmed that most stars have planets. Not some stars, not even most stars. We're talking about a near universal feature of how star systems form. Data from the Kepler Space Telescope alone confirmed over 2,600 exoplanets in a tiny sliver of sky, and the statistical models built from that data suggest there are more planets in our galaxy than there are stars. There could be 1 trillion planets in the Milky Way, possibly more. Of those planets, a significant fraction orbit within what astronomers call the habitable zone. That's the band of orbital distance where a planet is neither too hot nor too cold for liquid water to exist on the surface. Liquid water is the baseline condition we associate with life as we understand it. Estimates suggest there could be tens of billions of Earth-sized planets sitting inside habitable zones just in our galaxy. Tens of billions. On potentially trillions of worlds total, tens of billions have at least the right temperature range and the right basic conditions for life to have a fighting chance. And here's the thing most people don't realize when they picture this. The Milky Way isn't young. Our galaxy is approximately 10 billion years old. Earth is only about 4.6 billion years old. Life appeared here within the first billion years after Earth formed. That means if similar planets existed around earlier stars, they had a head start on us. Not a small head start. We're talking billions of years. A civilization that emerged on a planet just 1 billion years older than Earth would have had 1 billion years longer to develop technology, to expand, to spread across the stars. By comparison, we've had electricity for about 150 years. Think about that for a second. If a civilization had 1 billion-year advantage over us and developed even modest spacefaring technology, they could have crossed the entire Milky Way many times over by now. At just 1% of the speed of light, a spacecraft would cross the galaxy in about 10 million years. 1 million years is a rounding error against 10 billion. A civilization that started reaching for the stars when Earth was still a molten rock could have explored every corner of this galaxy and moved on to others before life on our planet had even figured out how to divide into 2 cells. So let's put this all together. Hundreds of billions of stars, most of them with planets. Tens of billions of these planets in habitable zones. A galaxy 10 billion years old, giving civilizations enormous windows of time to develop and expand. And beyond our galaxy, 2 trillion more galaxies following the same basic rules. The math here isn't subtle. It doesn't whisper that intelligent life might exist. It shouts that intelligent life should be everywhere. It should be so common that avoiding it should be harder than finding it. This is why astronomers describe the Fermi Paradox as genuinely paradoxical, not philosophically troubling, not merely surprising. Paradoxical, because when you line up the numbers honestly and follow them where they lead, the existence of widespread intelligent life isn't just possible, it's the expected outcome. You'd have to work hard to construct a model where it doesn't emerge somewhere, many times, across billions of years of cosmic history. And yet, look up at the night sky and you'll see stars. beautiful, ancient, silent. No signals cutting through the static, no megastructures dimming distant suns, no spacecraft visible on the edges of our solar system, no signals in the radio bands we've been monitoring for 60 years. Nothing confirmed, nothing verified. The universe looks, from where we're standing, essentially empty of anything communicating or expanding or building anything recognizable. That gap between what the numbers predict and what we actually observe is the Fermi Paradox. It's not a mystery born of insufficient data or poor telescopes. It's a mystery that gets sharper the more data we collect, because every confirmed exoplanet, every rocky world found in a habitable zone, every star system that turns out to harbor the right conditions makes the silence louder. Each discovery tightens the puzzle rather than loosening it. Some people hear these numbers and think the sheer scale of the universe guarantees we'll eventually find someone, but that's actually the wrong takeaway. The argument isn't that we'll find intelligent life eventually if we look long enough. The argument is that a universe this old and this large, operating by these rules, should have already produced civilizations so much older than ours that we should be the ones receiving their signals, not the ones searching. We should be looking up at a galaxy already lit with evidence. The math says the conversation should have started long before we showed up. It hasn't, and we don't know why. The size of the universe doesn't make the silence easier to explain. It makes it harder. Because every additional trillion galaxies, every additional billion habitable worlds, is another vote for life being common. Another reason we should already have our answer, another piece of evidence that something strange is going on. When you scale up the probability of life emerging to the scale of 2 trillion galaxies containing hundreds of billions of stars each, you're not dealing with a long shot anymore. You're dealing with what should be a near certainty, everywhere, constantly, which is what makes the quiet so strange. There's no signal. There's no trace. There's no echo of a billion-year-old civilization that should have had enough time to leave its mark on half the observable universe. We've built better and better instruments. We've scanned more of the sky with greater sensitivity, and the silence has held. Not weakened, not cracked, not even flickered. It's just there, steady and deep, behind every frequency we check. When you look at those numbers honestly, the question isn't whether intelligent life should exist. The question is how there could possibly be nothing out there making noise. In 1961, a young astronomer named Frank Drake sat down at a chalkboard in Green Bank, West Virginia, and wrote an equation that would shadow science for the rest of the century. The occasion was the first formal scientific meeting ever held on the question of extraterrestrial intelligence. A small group of researchers had gathered at the National Radio Astronomy Observatory, 11 people in total, including a young Carl Sagan, to think seriously about whether other civilizations existed and whether we could detect them. Drake wanted a framework, something that could organize the problem, break it into pieces, and give the conversation a structure. What he wrote on that chalkboard wasn't a solution. It was a map of the question itself. The Drake equation multiplies a series of factors together to estimate how many communicating civilizations might exist in the Milky Way right now. Each factor represents a step in the chain that goes from stars being born to a civilization capable of reaching across space with a radio signal. Work through them one at a time, and the logic is straightforward. Start with our star, the average rate at which new stars form in our galaxy. That one we can measure. Astronomers estimate roughly 1 to 3 new stars form in the Milky Way every year. Solid ground. From there, multiply by FP, the fraction of those stars that have planets. In Drake's time, this was almost entirely a guess. Today, thanks to the Kepler Space Telescope and decades of exoplanet research, we know the answer is close to 1. Virtually every star has planets. That's not a filter at all. It's almost universal. Then comes Ne, the number of planets in each system where conditions might be suitable for life. Rocky planets in habitable zones, close enough to a star to have liquid water but not so close that it boils away. Current estimates suggest something like 1 in 5 sun-like stars has a planet in that range. Still doing fine. The number is staying large. Here's where things start to get uncomfortable. The next factor is FL, the fraction of those habitable planets where life actually emerges. And nobody knows. We have exactly one data point: Earth. Life showed up here fairly quickly in geological terms, within a few 100 million years of the planet cooling enough to support it. Some researchers interpret that speed as evidence that life, given the right conditions, is almost inevitable. Others point out that one example tells you almost nothing statistically. FL could be close to 1. It could be 1 in a trillion. We genuinely have no idea. Then Fi, the fraction of life-bearing planets where intelligence evolves. Again, one data point. Earth existed for over 3 billion years before anything with a brain capable of abstract thought appeared, and multicellular life itself only arose once in Earth's history after single-celled organisms had dominated the planet for almost 2 billion years. Intelligence might be a near-certain outcome given enough time, or it might be an extraordinary accident that happened once on one planet and almost never happens anywhere else. Pick your assumption, and the equation's output shifts by orders of magnitude. After that comes FC, the fraction of intelligent civilizations that develop technology capable of communicating across interstellar distances. This one might seem safe. If intelligence evolves, surely technology follows. But consider that many intelligent species have walked this planet, elephants, dolphins, certain primates, without ever producing radio telescopes. The specific path from intelligence to technological civilization might be narrower than it looks. And finally, L, the average lifetime of a communicating civilization. How long do they last before they go silent, through self-destruction, technological stagnation, or something else entirely? This is the most critical variable in the entire equation, and it's the one we understand least. Drake's original estimate was fairly optimistic, somewhere in the range of thousands to millions of years. But if civilizations routinely destroy themselves within a few centuries of developing advanced technology, L could be very small. And a small L collapses everything. Drake ran his own estimates in 1961 and came out with a number between 10 and 10,000 communicating civilizations in the Milky Way. That was enough to make the search feel worthwhile. Enough to justify building radio telescopes and pointing them at the sky. The number felt plausible, encouraging even. But here's the thing. Most people don't realize about the Drake equation. Every variable you move changes the final answer by enormous amounts, and the variables get progressively harder to estimate as you move through the chain. The early factors, star formation rates, planets per star, we can actually measure. The later ones, starting with FL, are largely philosophical. You're not plugging in data, you're plugging in assumptions. And when you multiply a chain of uncertain assumptions together, the uncertainty doesn't just add up, it compounds. Change FL from 1 in 10 to 1 in a million. The answer drops by 5 orders of magnitude. Change Fi from near certain to extremely rare. Another collapse. Adjust L from 1 million years to 500 years. Suddenly, 10,000 civilizations becomes a fraction of one. And a fraction of one means we're probably alone in the galaxy. Same equation, different assumptions, completely opposite conclusions. Some researchers have run the numbers pessimistically and concluded that the expected value of communicating civilizations in the Milky Way is less than 1, meaning that even accounting for all the stars and all the planets and all the time available, the most likely outcome is that we're it. That calculation is not fringe science. It's a legitimate reading of the same equation Drake wrote in 1961. What makes this unsettling isn't that the equation gives you a bad answer. It's that it can give you almost any answer depending on what you believe about life and intelligence and the durability of civilizations. The equation doesn't tell you how many alien civilizations exist. It tells you precisely which questions you'd need to answer to know. And right now, we can't answer them. The equation itself doesn't give you an answer. What it gives you is a very precise map of everything we don't know, and every gap in that map is a place where the silence could be hiding. We've been listening, not casually, not passively, but with serious scientific equipment, real funding, and genuine intent. For more than 60 years, researchers have been pointing radio telescopes at the sky with one specific purpose: to find out if anyone else is transmitting. And the first thing you need to understand is why radio? Why not visible light, or X-rays, or something else entirely? The answer comes down to a concept called the water hole. In the radio spectrum, there's a quiet window, a frequency range where the natural background noise of the galaxy drops to near its lowest levels. Right in the middle of that window sit two very specific frequencies. One is produced by hydrogen atoms, the most common element in the universe. The other is produced by hydroxyl, the OH molecule. Hydrogen plus hydroxyl gives you water. Scientists reasoned that any civilization advanced enough to build a radio telescope would understand chemistry. They'd recognize those two frequencies immediately, and they'd understand why that particular window in the spectrum is the logical place to make contact. It's not arbitrary. It's the cosmic equivalent of a designated meeting spot. If you were trying to reach someone across the galaxy and you had to pick one place in the radio spectrum to leave a message, that's where you'd leave it. That reasoning was already in place by 1960 when astronomer Frank Drake pointed the Green Bank radio telescope in West Virginia at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened. He called it Project Ozma. For roughly 150 hours spread over several months, the telescope held its position, recording everything it picked up. Drake didn't seriously expect to hear anything on the first attempt, but someone had to go first. Project Ozma detected nothing unusual. No signal, no pattern, just the radio hiss of a universe that wasn't talking. The search had officially begun, and already the silence was the loudest thing in the data. Over the next decade and a half, efforts expanded. More telescopes, more targets, more frequency ranges. The scientific community slowly organized itself around the possibility that this was worth doing systematically. And then, on the night of August 15, 1977, something happened. A volunteer astronomer named Jerry Amon was reviewing data from the Big Ear telescope at Ohio State University. The telescope had been scanning automatically, recording signals in real time. When Amon reached one particular stretch of data, he saw something that didn't look like anything he had seen before. A strong narrowband signal, rising and falling in intensity, exactly the way a signal from a distant point source would. It matched nearly every characteristic that SETI scientists said to look for. Amon circled it on the printout and wrote one word in the margin. Wow. The wow signal lasted exactly 72 seconds. That was the amount of time a fixed point in the sky took to drift through Big Ear's beam. Then it was gone. Researchers pointed every available instrument back at that patch of sky. They searched on the same frequency at different frequencies across weeks and months and eventually years. The signal never repeated. It has never been fully explained. No natural source has been identified that convincingly accounts for it, and no artificial source has ever been confirmed. It came once. It looked like exactly what you'd hoped to find, and it never came back. Think about that for a second. In 60 years of searching, the single most compelling candidate we've ever recorded lasted 72 seconds and then disappeared into silence. That was 1977. Here's where things get uncomfortable. In the decades since, the search only got bigger and more sophisticated, and the result stayed the same. SETI at Home launched in 1999 as a way to bring the public directly into the search. The project distributed radio telescope data from the Arecibo Observatory to millions of volunteers around the world, using the idle processing power of home computers to analyze it. For 14 years, the project collected and analyzed that data. It found billions of candidate detections. Billions. Brief spikes, unusual patterns, signals that didn't immediately look like interference. Every single one of them, after analysis, turned out to be explainable. Radio frequency interference from satellites, from cell towers, from aircraft, from equipment. Not one confirmed signal of extraterrestrial origin, not one that survived scrutiny. Then in 2015, the Breakthrough Listen initiative launched with $100 million in funding and a 10-year mission to conduct the most thorough search in history. It has access to some of the most powerful radio telescopes on Earth. It covers more frequency ranges, more targets, and more sky than any previous effort. Its stated goal is to survey the 1,000,000 closest stars, the 100 nearest galaxies, and the entire plane of the Milky Way. The results so far have been exactly what every previous project found. Nothing confirmed, no repeating signal, no pattern that survives as artificial once you've eliminated every other possibility. No message, no beacon, no sign that anyone is transmitting into the dark, hoping something like us might be listening back. The waterhole has stayed quiet. The logical meeting spot in the spectrum has had no meetings. Here's the thing. Most people don't realize about what that silence actually represents. These searches aren't trivially easy to explain away. Breakthrough. Listen is genuinely sensitive enough to detect the kinds of signals we ourselves produce. Radar, broadcast transmissions, deliberate directional beams from a substantial distance. We're not missing things because we lack the technology. We're missing things because, as far as every instrument we've pointed at the sky can determine, there's nothing there to find. 60 years of searching with the best equipment we've ever built, and the answer so far is the same as it was in 1950 when Fermi asked his question over lunch. Nothing. One of the first explanations people reach for is the simplest one. Maybe life is just extraordinarily difficult to get started. Not difficult in the way building a bridge is difficult, or even difficult in the way landing on the moon was difficult. Difficult in a way that might mean it only happened once across the entire observable universe. That's the idea at the core of the rare Earth hypothesis, and once you actually walk through the conditions that had to align for Earth to produce intelligent life, it stops sounding extreme. It starts sounding almost obvious. Here's the thing most people don't realize when they look at Earth and assume it's a typical planet. It isn't. Not even close. Earth isn't a generic rocky world sitting in a habitable zone. It's the product of an almost absurd sequence of improbable events stacked on top of each other, each one necessary, none of them guaranteed. Remove any single piece of that sequence, and you probably don't get us. You might not get anything at all. Start with the star. Our sun is the right type, a G-type yellow dwarf, stable enough to burn at a consistent output for billions of years without dramatic flares stripping the atmosphere off its planets. Most stars in the galaxy aren't like this. About 70% are red dwarfs, smaller and dimmer, which sounds harmless until you realize that planets in their habitable zones are so close that they're tidally locked. One side permanently facing the star, one side permanently in darkness. They're also prone to violent stellar flares that can bombard nearby planets with radiation intense enough to strip away any developing atmosphere. Life needs time. Billions of years of time. A star that flares constantly or burns out in a few billion years doesn't give life the runway it needs. Then, there's the moon. Ours is unusually large relative to our planet, so large that astronomers suspect it shouldn't exist at all without the specific conditions that created it. About 4.5 billion years ago, a body roughly the size of Mars, which scientists call Theia, collided with the early Earth at exactly the right angle and speed to tear off a massive chunk of material. That debris eventually coalesced into the moon. The timing and geometry of that collision were not inevitable. It was a cosmic accident. But without it, Earth wouldn't have a large stabilizing moon. And without that stabilizing moon, Earth's axial tilt would wobble chaotically over millions of years, swinging from extreme to extreme and producing climate conditions so violent that stable ecosystems might never have had the opportunity to develop. Plate tectonics is another one. Earth's crust is broken into massive plates that slowly drift, collide, and dive beneath each other. This process cycles carbon and other nutrients back into the atmosphere over geological timescales, acting as a long-term thermostat that regulates the planet's temperature. It also drives volcanic activity that replenishes the atmosphere. Without plate tectonics, the surface of a planet tends to lock up. Venus is a good example. Similar size to Earth, similar distance from the Sun, and no functioning plate tectonics. The result is a runaway greenhouse world with surface temperatures over 450 degrees Celsius and an atmosphere thick enough to crush a spacecraft. Earth's tectonic activity wasn't guaranteed just because the planet formed at the right distance from the Sun. It required the right internal composition, the right amount of heat, and again, the right kind of cosmic luck. Then consider Jupiter. The largest planet in our solar system sits far enough out that its immense gravity acts as a kind of shield, pulling in or redirecting asteroids and comets that might otherwise rain down on the inner solar system. Early in Earth's history, this shielding allowed conditions to stabilize enough for life to take hold. Without Jupiter's gravitational presence in roughly its current position, the bombardment rate on Earth would have been substantially higher and more sustained. Life might have been repeatedly wiped out before it could establish a foothold. That's not speculation. It's orbital mechanics. And Earth's magnetic field, generated by the movement of liquid iron in the planet's outer core, this magnetic field deflects the solar wind, a constant stream of charged particles flowing off the Sun. Without it, that solar wind would gradually strip away the atmosphere over millions of years, the way it did with Mars. Mars once had a thicker atmosphere and likely liquid water on its surface. It lost its magnetic field billions of years ago, and the solar wind did the rest. Today it's a frozen, irradiated desert. So all of those things had to happen correctly, and then, even after all of that, life still took an enormous amount of time to do anything interesting. The first microbial life on Earth appeared around 3.5 billion years ago, possibly earlier. For the next 2 billion years, life stayed simple. Single-celled organisms, prokaryotes, dominated the planet almost exclusively for longer than the current age of the solar system. The jump from simple single-celled life to the eukaryotic cells that eventually produced complex organisms appears to have happened essentially once, a specific merger between two types of prokaryotes that gave rise to cells with a nucleus. That event took almost 2 billion years to occur, and there's no particular reason to think it happens easily or repeatedly on other worlds. Multicellular life came later still, and it too seems to have appeared only once before diversifying. From that point, another several hundred million years passed before anything resembling an animal existed, and several hundred million more before anything with a brain sophisticated enough to ask questions about the universe appeared on the scene. What that timeline tells you is something genuinely sobering. Even on a planet with perfect conditions, the right star, the right moon, the right tectonics, the right magnetic field, the right Jupiter, life still took more than 3 billion years to get from microbes to minds. 3 billion years. That's not a gap you can bridge by tweaking the chemistry. That's a gulf. And the transition from simple life to complex life required specific, improbable events that may not be remotely likely to repeat on other worlds. This is where the distinction between simple life and intelligent life becomes critical. The two are not the same question, and conflating them has led a lot of people to premature optimism. It's entirely possible that simple microbial life is relatively common in the universe. Wherever liquid water exists in stable conditions for long enough, chemistry might find a way. The real question isn't whether life starts. It's whether life ever gets complicated, whether it ever builds brains, whether it ever looks up. And the honest answer, based on everything we know about Earth, is that the answer might be almost never. The conditions required don't just need to be good, they need to be perfect, sustained over billions of years, and punctuated by the right sequence of accidents at the right moments. Change the mass of Theia. Change Jupiter's orbital position by a few %. Remove the magnetic field a billion years early. Slow the development of plate tectonics. Any of those changes, and this planet might be as quiet as Mars. Maybe the universe is full of oceans and the right temperatures and rocky planets, but completely empty of anything that breathes or thinks. And Earth is the single impossible exception. There's a concept in astrobiology that, once you really understand what it's saying, you can't quite shake. It was first laid out in 1998 by an economist named Robin Hanson, which is already a little unusual. Most of the ideas we've talked about tonight come from physicists and astronomers. Hanson approached the silence from a different direction, from the logic of probability and expected outcomes. And what he arrived at is something that cuts much deeper than most scientific hypotheses tend to cut. He called it the Great Filter. Here's the core logic. The galaxy is roughly 10 billion years old. That's an almost incomprehensible span of time, even if intelligent spacefaring civilizations are rare. Even if only 1 in a billion planets ever produces them, the math still says they should exist in enormous numbers by now. And once a civilization figures out how to leave its home star system, the entire galaxy is colonizable within a few tens of millions of years. That sounds like a long time, but it's less than 1% of the galaxy's current age. If interstellar travel is possible, even slow interstellar travel, One sufficiently motivated civilization starting a billion years ago should have already reached every corner of the Milky Way. We should be surrounded by evidence of that expansion, megastructures, signals, some kind of footprint left by whoever got here first. There's nothing, no footprint, no signal, no sign of anyone having passed through. So Hansen's argument is straightforward. Either the path from simple chemistry to a spacefaring civilization has some step that is so improbable it almost never happens, or civilizations that get close to that stage don't last long enough to make the leap. One way or another, something is filtering them out. Something is stopping them. The galaxy should be full by now, and it isn't. That means something is in the way. That something is the great filter. Now the next question is obvious. Where is it? Because that question has a very different answer depending on whether you want to sleep tonight. There are several places the filter could be hiding. Let's start at the beginning. The first candidate is abiogenesis itself, the moment when chemistry becomes biology. We still don't fully understand how life got started on Earth. We know it happened because we're here. We have fossilized evidence of life going back at least 3.5 billion years, possibly closer to 4 billion. But the specific mechanism, the exact sequence of chemistry that crossed the line from self-replicating molecules to something we'd recognize as a living cell, that remains genuinely unsolved. It's possible that this transition requires such a precise and unlikely combination of conditions that it almost never happens. If abiogenesis is the filter, then most planets go through billions of years of the right temperatures and liquid water and organic chemistry and never produce a single living cell. Life itself is the miracle, and it happens almost nowhere. But let's say abiogenesis isn't the barrier. Let's say simple life gets started fairly often. There's still a second candidate, and it's one that took an almost unbearable amount of time even on Earth. The jump from prokaryotes to eukaryotes. Prokaryotes are simple single-celled organisms with no distinct nucleus, bacteria and archaea. For roughly 2 billion years after life appeared on Earth, that was all there was. 2 billion years of nothing but simple cells. Then, around 2 billion years ago, something happened. One prokaryote absorbed another in a way that was somehow stable and mutually beneficial, and the result was a eukaryotic cell. A cell with a nucleus, with internal structure, with a fundamentally different level of complexity. Everything you can see with the naked eye is built from eukaryotic cells. Every plant, every animal, every fungus. That transition happened once in the entire history of Earth, after 2 billion years of waiting. That's not nothing. That's potentially a filter so improbable that the vast majority of planets with life never cross it. Then there's the jump to multicellular life. Single-celled eukaryotes existed for hundreds of millions of years before cells began organizing into coherent multicellular organisms. That transition happened multiple times on Earth, which suggests it's not quite as rare, but it still required vast stretches of time and very specific conditions. And each of these steps builds on the previous one. You need abiogenesis before you can get prokaryotes. You need prokaryotes before you can get eukaryotes. You need eukaryotes before you can get multicellular life. The whole sequence is dependent, and any step that fails propagates that failure through everything downstream. And then, even after multicellular life, you need intelligence, complex nervous systems, brains capable of abstract thought, language, the ability to model the future and plan for it. On Earth, animals have been around for roughly 600 million years. Recognizably, human intelligence has existed for maybe 50,000. That ratio alone should give you pause. Intelligence might be something that takes an enormous amount of time to produce, even when the biological substrate is already in place. Or it might be something that requires such a specific evolutionary pressure that it's essentially a fluke. Here's the thing most people don't realize about any of these candidates. It doesn't matter which one is the filter. What matters is that at least one of them must be almost impossibly difficult. Not just hard, not just rare, essentially impossible. Because if all of these steps were merely unlikely, 1 in a million, say, you'd still expect the galaxy to be crawling with intelligent life given the number of planets and the time available. For the galaxy to be this quiet, something in the chain has to be so improbable that it almost never succeeds. Somewhere along the path from hydrogen and helium to a civilization that can build spacecraft, there's a wall that almost no one gets over. And that brings us to the part that should genuinely unsettle you. The filter is either behind us or ahead of us. Those are the only two options. If it's behind us, that means one of the steps we've already cleared, abiogenesis, the eukaryotic transition, the emergence of intelligence, something, was the near impossible step. We made it through. The wall is in our past. And if that's true, it's extraordinary news. It means we're extraordinarily rare, possibly unique in the galaxy, possibly among the first intelligent civilizations to have ever existed. That's a strange kind of luck to contemplate. But here's the other possibility. What if none of those early steps were the real filter? What if life gets started reasonably often? What if simple cells upgrade to complex cells fairly regularly? What if intelligence, given enough time, tends to emerge wherever the conditions are right? If all of that is true, then the great filter isn't behind us. It's somewhere ahead. And that changes everything. Because if the filter is ahead of us, it means civilizations routinely make it to roughly where we are. Technology, industrialization, spaceflight on the horizon, and then fail to get any further. Something kills them. Something stops them from becoming spacefaring. Maybe it's a natural catastrophe they can't predict. Maybe it's a resource ceiling they can't escape. Maybe it's something they build that they can't control. Whatever it is, it operates consistently enough and completely enough that none of the civilizations that reach this level ever make it to the stars. They disappear, and they disappear before they leave any trace we can detect from here. The way you figure out which version is true matters enormously. Think about what it would mean to discover microbial life on Mars, or in the ocean beneath the ice of Europa, or in the atmosphere of Venus. Most people would think that's the best possible news. Evidence of life beyond Earth. Proof that we're not alone in the most fundamental sense. But Hansen's framework flips that intuition completely. If simple life is common, if it arose independently on multiple worlds right here in our own solar system, then abiogenesis isn't the filter. Neither is the emergence of early biology. And that means the filter is still out there somewhere in our future, waiting for us. The more life we find nearby, the worse the news is about what's coming. That's not a comfortable thought. It's meant to be unsettling. The great filter is one of those concepts that reorders how you look at the question. It doesn't tell you what the answer is. What it does is tell you that one of two things must be true, and both of them are profound in ways that are hard to sit with. If the filter is behind us, we are lucky beyond all comprehension. And if it's ahead of us, we're probably not going to make it either. And here's where things get genuinely unsettling. Everything we talked about in the last section assumed the filter was somewhere behind us, something in our deep past, the first cell, the first nucleus, the first brain, that was so improbable it essentially never happened anywhere else. That's the comforting version, because if the hardest step is already behind us, we're the lucky ones. We cleared it. We made it through. But there's another possibility, and it's the one that keeps serious researchers up at night. What if the filter isn't behind us at all? What if it's right in front of us, and every civilization that reaches our level of development hits it and fails? What if the silence in the galaxy isn't the silence of life that never started, but the silence of civilizations that got exactly as far as we have and then didn't make it any further? Think about what happens when a civilization develops technology, not primitive technology, not fire in the wheel. Real technology, the kind that can reshape a planet, the kind we started building in the 20th century. Here's the thing most people don't realize. The same level of intelligence that produces the science to reach the stars also produces the tools to make extinction possible. And those two things arrive at essentially the same moment. We discovered nuclear fission in 1938. Within 7 years, we had built bombs capable of leveling entire cities. Within 2 decades, we had enough warheads to end human civilization several times over. The doctrine of mutually assured destruction, the idea that any nuclear exchange would be catastrophic for both sides, is the only thing that has kept those weapons from being used at full scale. And that doctrine depends entirely on every decision maker on every side behaving rationally under maximum pressure every single time, forever. One miscalculation, one system failure, one leader in the wrong state of mind at the wrong moment. That's the margin we're operating on, and we've come close. In 1983, a Soviet early warning system incorrectly detected 5 incoming American missiles. The officer on duty, Stanislav Petrov, chose to report it as a system malfunction rather than a genuine attack. He was right. But if he'd followed protocol, if he'd reported it as a real launch, the retaliation sequence would have begun. No one would have stopped it in time. The world didn't end that night because one man made a judgment call that happened to be correct. That's not a comfortable safety margin for a species that wants to survive long enough to reach other stars. Nuclear war is just the most obvious mechanism. Climate change is slower, but in some ways more insidious because it doesn't announce itself with a countdown clock. Industrial civilization runs on energy, and for 200 years that energy has come from burning carbon that was sequestered over hundreds of millions of years. The atmospheric consequences build gradually, almost imperceptibly on a human timescale, right up until they become impossible to reverse. A civilization that doesn't recognize the danger until the feedback loops are already running may find that correcting course requires a level of global coordination it simply isn't built to achieve. And if industrial civilization collapses before a species becomes truly spacefaring, it may never get a second chance. Resources are finite. Some of them, once depleted, don't come back on any timescale that matters. Then there's biotechnology. We're already at the point where a small, well-resourced group could engineer a pathogen with targeted lethality using tools that fit in a modest laboratory. That capability is only going to become more accessible. A naturally occurring pandemic like the one in 2020 tested global institutions and response systems in ways that revealed significant fragility. An engineered pathogen designed specifically to spread before symptoms appear and optimized for maximum lethality could move faster than any containment system we currently have. The same gene editing technology that might one day eliminate inherited disease could, in the wrong hands, produce something civilization doesn't recover from. And then there's artificial intelligence. This one is different from the others because the others are threats we can at least recognize and attempt to manage. A sufficiently advanced AI that outpaces human control doesn't have to be malicious to be catastrophic. It just has to be optimizing for something other than human survival. We're already building systems that make consequential decisions faster than human oversight can track. The trajectory points towards systems that are more capable than the humans attempting to oversee them. At some point in that progression, the question of who is actually in control stops having a clear answer. What makes the current moment particularly acute is the compression of timescales. For most of human history, technological change moved slowly enough that societies could adapt. A blacksmith's apprentice might learn tools recognizable to his ancestors, but that pace has collapsed. The interval between the first airplane and nuclear weapons was 37 years. The gap between the first programmable computer and artificial general intelligence may span less than a century. This acceleration means civilizations don't have much time to develop the wisdom institutions needed to manage their own power. The stakes escalate faster than adaptation can keep pace. Regulatory frameworks routinely lag behind innovation by years or decades. International agreements move at bureaucratic speeds, and the technologies don't wait for coordination. Here's what makes this genuinely different from the natural threats that species have always faced. A meteor can kill you. A volcanic winter can kill you. A new disease can kill you. But none of those forces also give you the ability to build civilization. Nuclear technology, biotechnology, artificial intelligence, each of these is both the source of tremendous capability and the source of potential extinction. The same package. You can't develop one without the other. And you have to survive wielding both simultaneously. So ask yourself, what does a civilization look like in the window between developing these technologies and either mastering them or being destroyed by them? It looks like us, right now. This specific moment in history. We have nuclear weapons. We have gain-of-function research and biosafety labs. We have AI systems developing faster than regulatory frameworks can keep up. We have a climate system responding to 2 centuries of industrial output. We are inside the gauntlet. We're not approaching it. We're in it. And the Fermi Paradox suggests we might look at the galaxy and ask, where is everyone who made it through? The answer coming back is silence. Not a little silence, total silence. Billions of stars, billions of years, and nothing. No signals, no megastructures, no evidence that any civilization has ever reached the other side of this particular bottleneck and spread out into the cosmos. That could mean civilizations almost never arise. That's the rare Earth answer. The great filter behind us. But it could mean something else. It could mean that civilizations arise with some regularity, develop technology with some regularity, hit this exact phase, the nuclear age, the biotech age, the AI age, and then, with depressing consistency, don't survive it. Not because they were stupid, not because they didn't understand the risks, but because surviving requires a kind of species-level wisdom and coordination that intelligence alone doesn't automatically produce. You can be brilliant and still not be able to get 100 countries to agree on something before it's too late. That's the version of the great filter that makes the silence feel different. Not a cosmic accident. Not an improbable chemistry problem. A pattern. Civilizations reaching exactly where we are, and then going quiet. There's an astronomer named Carl Sagan who spent much of his life arguing that the existence of other civilizations would be profoundly reassuring, not just as company, but as evidence that a technological civilization can survive its own adolescence. If someone made it through, that means it's possible. Every signal we detected would be proof that there's a path. The silence implies the opposite. It implies there might not be one, or that finding it requires something we haven't managed to develop yet. You're watching this in a moment that, by any historical measure, is a genuinely critical juncture. The technologies that define the next century are being built right now. The decisions being made in the next few decades about how to manage nuclear arsenals, how to regulate biotechnology, how to govern artificial intelligence. Those decisions matter in ways that extend far beyond any one country or any one generation. They matter in the way that determines whether this civilization is one of the ones that makes it through or one of the ones that contributes to the silence. Seen from that angle, the silence in the galaxy stops feeling like an academic puzzle and starts feeling like something closer to a warning. But let's set aside biology and civilizations for a moment and talk about physics, because even a civilization that survives every internal threat still has to deal with the basic structure of space. Here's the thing most people don't realize when they think about interstellar travel. The problem isn't just that space is big, it's that the distances involved are so extreme that they break our intuitions completely. The nearest star system to our own is Alpha Centauri, sitting about 4.37 light-years away. That sounds like a number. It doesn't feel like one. A light-year is the distance light travels in an entire year, moving at 186,000 miles per second. Multiply that by 4.37 and you get roughly 25 trillion miles. That's not a commute. That's not a voyage. That's a different category of distance than anything human civilization has ever attempted. Our fastest spacecraft right now is the Parker Solar Probe. At its peak, it hits about 430,000 miles per hour. That's fast enough to cross the United States in under a second. By human standards, it's extraordinary. In cosmic terms, it's barely moving. If you pointed the Parker Solar Probe directly at Proxima Centauri and let it run, it would take approximately 6,700 years to arrive. Think about that for a second. 6,700 years. All of recorded human history spans about 5,500 years. Our fastest machine would need longer than that just to reach the nearest star. And that's the nearest one. The galaxy is 100,000 light-years across. The math gets incomprehensible very quickly. So the question becomes, what would it actually take to cross that distance in any meaningful time frame? The answer is that you'd need to travel at a significant fraction of the speed of light. Not a tiny fraction, a significant one. 10%, 20%, ideally higher. And here's where the physics becomes genuinely brutal. Nothing with mass can reach the speed of light. That's not an engineering limitation waiting to be solved. That's a fundamental constraint built into the structure of space-time itself. As you accelerate toward the speed of light, the energy required to keep accelerating increases without limit. You'd need infinite energy to reach it. The speed of light isn't a barrier you can break through with a better engine. It's the wall at the end of the universe. So let's go through the options. Chemical rockets, the kind we've been using since the 1960s, are completely inadequate. The best chemical rockets we've ever built can push a spacecraft to maybe 40,000 miles per hour under ideal conditions. That's 0.006% of the speed of light. To reach even 1% of light speed with chemical propulsion, you'd need a fuel tank so massive it collapses under its own gravity. It doesn't work, not even close. Nuclear pulse propulsion is more interesting. The concept, developed seriously under Project Orion in the 1950s and 60s, was to detonate nuclear bombs behind the spacecraft and absorb the shockwave with a massive plate. Computer models suggested this could theoretically accelerate a spacecraft to several percent of light speed. That's actually meaningful for interstellar travel, but the practical problems are enormous. You'd need thousands of nuclear warheads. The radiation would be intense enough to be a serious concern. Getting such a spacecraft off the ground would require detonating nuclear devices in or near Earth's atmosphere, which is politically and legally impossible under current international treaties. The engineering is staggering, and the public reaction would be something to behold. Fusion drives sound promising on paper. The sun runs on fusion. If we could replicate that process in a compact engine, the energy density would be extraordinary, and the fuel, hydrogen, is the most abundant element in the universe. The problem is that we haven't achieved controlled fusion. Not in a power plant, not in a laboratory, not anywhere. Researchers have been working on this problem for over 70 years. We're still not there. Even optimistic projections put a practical fusion reactor decades away. And a fusion rocket is a far harder engineering problem than a stationary power plant. You need the reaction to be controllable, efficient, and compact enough to fly through space. Nobody knows how to do that yet. Antimatter engines are even further out. When matter and antimatter collide, they annihilate completely, converting all their mass directly into energy, according to E equals mc squared. That's the most efficient energy release physically possible. In principle, a small amount of antimatter could generate enormous thrust. In practice, the problem is production. We can create antimatter in particle accelerators, but only in microscopic quantities. The total amount of antimatter ever produced in human history wouldn't power a light bulb for more than a few minutes. To fuel an interstellar spacecraft, you'd need kilograms or possibly tons. At current production rates, generating that much antimatter would take longer than the current age of the universe. And even if you had it, storing it without touching any ordinary matter is an engineering challenge so severe that a single containment failure would produce an explosion comparable to a nuclear weapon. The most genuinely promising near-term concept is Breakthrough Starshot, announced in 2016. The idea is to use a massive ground-based laser array to push a tiny light sail, a spacecraft the size of a microchip weighing about a gram, with a sail a few meters across. The laser accelerates it over a few minutes to roughly 20% of the speed of light. At that speed, it could reach Proxima Centauri in about 20 years. That's the most credible proposal on the table right now. But here's where things get uncomfortable. The spacecraft is so small it can carry almost no instrumentation. It can't carry enough power to send much data back to Earth. It cannot slow down. It would scream past the Proxima Centauri system at 20% light speed, with a window of maybe a few hours to observe anything before it's gone forever. And any signal it sends home takes 4 years to arrive. You'd wait 20 years for it to get there, and 4 more years to hear what it saw. That's the optimistic scenario. Here's the thing that cuts through all of this. Every one of these proposals faces the same underlying reality. The universe seems almost calibrated to make interstellar travel not just difficult but nearly impossible. The distances are so vast that even light takes years to cross them. The physics prevents you from matching light's speed. The energy required to get close is beyond anything we can currently conceive of producing. And the proposals that come closest to working either can't carry meaningful payloads, can't slow down on arrival, or depend on technologies decades away from realization. A civilization doesn't just need the will and the survival instincts to reach for the stars. It needs to overcome a set of physical constraints that the universe has placed between every star system and every other one. The universe isn't just large, it's built in a way that seems almost deliberately engineered to keep everything in it from ever reaching everything else. There's another dimension to this problem that doesn't get enough attention: And it has nothing to do with whether civilizations exist or survive or want to communicate. It has to do with time. Specifically with how absurdly brief our window of existence has been compared to the age of the galaxy itself. The Milky Way is roughly 10 billion years old. Let that sit for a second. 10 billion years. Intelligent life on Earth, by the most generous estimates, has existed for about 50,000 years. Written records go back only around 5,500 years. And the era of radio broadcasting, the era where we've actually been generating electromagnetic signals capable of escaping the planet, spans barely 100 years. So out of 10 billion years of galactic history, we've been making detectable noise for roughly the last 100 of them. That's not a small number relative to a human lifetime. It's a rounding error relative to the age of the universe. Here's what that actually means in practical terms. Our radio signals travel at the speed of light. In 100 years of broadcasting, those signals have reached a sphere maybe 200 light-years across. The Milky Way is 100,000 light-years across. We've essentially whispered into one corner of an enormous stadium and then asked why nobody on the other side responded. But the distance problem isn't even the most troubling part. The timing problem might be worse. Think about what a civilization's detectable window actually looks like. A species develops intelligence, builds technology, generates signals, and then, at some point, either collapses, goes silent, or disappears. Based on everything we discussed about the Great Filter and civilizational self-destruction, that window might be relatively short. A few thousand years, maybe tens of thousands. Against a 10 billion year galactic backdrop, a civilization with a 10,000-year lifespan occupies 0.0001% of available time. Two civilizations would both have to exist during that sliver within a distance that allows signals to cross between them at the same moment. The odds of that overlap are staggering. Imagine a civilization that arose on a planet 500 light-years away, roughly a billion years ago. They were intelligent. Maybe they were curious about the stars. They built things, studied the sky, wondered if anyone else was out there. And then, for whatever reason, they were gone. Their signals radiated outward across the galaxy for millions of years. But we weren't here yet. The Earth was a ball of cooling rock crawling with single-celled organisms. By the time our species existed to listen, their transmissions had long since passed us by, diffused into background noise, impossible to distinguish from anything natural. We'll never know they were there. There's no record we could ever access. This pattern might repeat countless times across the Milky Way. Civilizations bloom and fade, their radio waves expanding outward into the dark, reaching out to neighbors who haven't yet evolved the capacity to listen. The galaxy becomes a graveyard of missed connections, each extinction event erasing one more potential contact window. We're searching for contemporaries in a universe where contemporary existence itself might be the rarest condition of all. Now flip the scenario. Some civilization on a planet orbiting a star 300 light-years away might be looking toward Earth right now, or rather looking toward where Earth was 300 years ago, because that's how long the light takes to reach them. In 1724, Earth had no radio signals, no satellites, no industrial emissions visible in the atmospheric chemistry. From their perspective, Earth is a silent, unremarkable rocky planet with some oxygen in its atmosphere and nothing particularly interesting going on. They might have checked, logged it as inert, and moved on centuries before we started making any noise worth noticing. This is what makes the timing problem so quietly devastating. It's not that the universe is empty. It might be that the universe is full of civilizations that simply don't exist at the same moment we do. Each one rises, burns for a cosmically brief instant, and fades. And the gaps between those instants, measured in millions or hundreds of millions of years, are vast enough to swallow every signal, every probe, every attempt at contact without trace. There's a stranger version of this that's worth sitting with. Advanced civilizations might have visited Earth, not in the era of ancient Egypt or Mesopotamia, but genuinely long ago, before multicellular life, before complex nervous systems, before anything on this planet was capable of forming a memory of the encounter. If a probe or a vessel passed through our solar system 600 million years ago, what would it have found? Simple ocean life, microbial mats, nothing that could observe, record, or remember being observed. If something extraordinary happened, a forest might have burned. Some ancient species of jellyfish might have scattered in confused directions. And that's it. The event would have left no record we could ever interpret. The visit, if it happened, is simply gone. This reframes the Fermi Paradox in a way that's harder to dismiss than most solutions. We tend to ask the question as if the galaxy is a stage and all civilizations exist on it simultaneously, waiting to be found. But it's more accurate to think of it as a stage where actors come and go across billions of years, each performing in an empty theater, their voices echoing into a hall that won't have an audience for another 100 million years. The performances happen. They're real. But nobody's there to hear them. Our search for extraterrestrial intelligence assumes we're contemporaries with whatever's out there. SETI listens for signals arriving right now from civilizations transmitting right now. But given the timescales involved, that assumption might be the most fragile one we're making. The galaxy is old enough, and civilizations may be brief enough that the honest answer to Fermi's question might simply be, they were there, but we weren't. But what if they're out there? They know we're here, and they're simply choosing not to contact us. Not because they're indifferent, but because contact itself might be the most dangerous thing you can do. This is the dark forest hypothesis, and it comes from a place you might not expect. Chinese science fiction author Liu Cixin laid it out in his 2008 novel, The Dark Forest. And the idea is elegant in the most unsettling way possible. It doesn't require the universe to be empty. It doesn't require aliens to be too far away or too different to find us. It just requires them to be rational. And if they're rational, the logic that follows is almost impossible to escape. Here's the core of it. Imagine the universe as a dark forest. Every civilization is a hunter, moving through the trees as quietly as possible, armed and alert. They can hear things, movements, sounds, but they can't see clearly, and they don't know what else is in the forest with them. Now imagine another hunter makes a noise, lights a fire, shouts into the dark. What does a rational hunter do? They don't walk toward the sound with open arms. They don't assume the other hunter is friendly. They eliminate the threat before it can become one. That sounds extreme, but let's walk through why the logic actually holds. Start with resources. The universe is vast, but resources within any given region of space are finite. Stars, planets, energy, all of it is limited. Any civilization that has been around long enough to achieve interstellar capability has also been around long enough to understand resource competition. They know that another civilization, given enough time, could grow to compete with them for exactly the things they need to survive. Now add the second piece. You cannot verify intentions. This is the crucial part most people skip over. Let's say an alien civilization sends us a message that says, in perfectly translated terms, "We come in peace. We want to share knowledge. We mean you no harm." How do you know that's true? You can't visit them to check. You can't verify their history or their political structure or whether the message was even sent by whoever claims to be in charge. You have one signal and no way to confirm anything about the civilization behind it. Across interstellar distances, with communication delays measured in years or decades, trust cannot be established with any certainty. And in a situation where being wrong about someone's intentions could mean the end of your civilization, caution isn't paranoia, it's survival. Add the third piece, the first strike advantage. If two civilizations discover each other and one of them decides the other is a potential threat, the rational move is to act before the other civilization grows strong enough to be dangerous. Waiting is the worst strategy. Waiting gives the other side time to develop better weapons, faster ships, more resources. In a universe where interstellar travel takes centuries or millennia, a civilization that acts decisively and early has an enormous advantage over one that hesitates. Put all three pieces together, and you get the Dark Forest. Every civilization that understands these dynamics has strong incentive to stay hidden and to eliminate any civilization that draws attention to itself. Not out of malice, out of cold, rational self-interest. You don't have to reach far for human parallels. Look at what happened when different civilizations made contact throughout our own history. When Spanish conquistadors arrived in the Americas, the encounter was not a meeting of equals trading knowledge. It was catastrophic for one side. The Aztec Empire, with millions of people and centuries of accumulated culture, collapsed within 2 years of Spanish contact. The Inca fell shortly after, not because the indigenous peoples were unintelligent or unprepared, but because the power differential was decisive and the more powerful party had no compelling reason to treat the encounter as a partnership. They had everything to gain and very little reason to hold back. Now imagine that dynamic scaled to the difference between a civilization that has been developing for 100 years and one that has been developing for 100,000 or 1,000,000. The gap in capability would make the Spanish-Aztec encounter look like a minor disagreement. A civilization that advanced would not need to negotiate or bargain or threaten. It could simply act, and the less powerful civilization would have no meaningful response. The Dark Forest hypothesis says this is what the galaxy already looks like. Every sufficiently advanced civilization has run this calculation. They've concluded that silence is safety and that anything announcing itself is either naive, a trap, or not yet dangerous enough to worry about, but will be eventually, so you eliminate it. Not personally, not maliciously. The way you might remove a weed from a garden before it becomes something harder to deal with. Here's where things get uncomfortable for us specifically. We have not been quiet. For over a century, we've been leaking radio signals into space, television broadcasts, military radar, satellite communications, all of it radiating outward at the speed of light in every direction. We didn't choose to do this. It was simply the byproduct of building a technological civilization. But from the outside, it looks like exactly the kind of noise the Dark Forest says you should never make. And we went further. In 1974, astronomers transmitted the Arecibo message directly toward a star cluster roughly 25,000 light-years away. The message was designed to be understood, a deliberate, structured signal announcing our existence, our location, our biology. In 2008, a transmission called A Message from Earth was beamed toward Gliese 581c, a planet about 20 light-years away. We have done this more than once. We have knowingly and deliberately pointed a signal at a specific location in the galaxy and said, "Here we are." If the Dark Forest hypothesis is correct, this is about the worst thing you can do. Now there are objections worth considering. One is that our signals are weak. By the time a radio broadcast from Earth reaches even a nearby star system, it's incredibly faint. Background noise competing against the output of the sun itself. Detecting us would require technology significantly beyond our own. But that's exactly the kind of technology a civilization dangerous enough to be a threat would possess. The civilizations that can't detect us are probably not the ones you need to worry about. Another objection is that the hypothesis requires every civilization in the galaxy to independently reach the same strategic conclusion. That's a lot of independent agreement, but consider that the logic isn't cultural, it's mathematical. Resource competition, the impossibility of verifying intentions, the first strike advantage. These aren't values or beliefs. They're structural features of any universe where multiple civilizations share finite space. You don't need to coordinate to reach the same answer when the math points in only one direction. The last objection is the most hopeful one. Maybe the civilizations that survive long enough to become dangerous also develop the wisdom to resist this logic. Maybe there's a developmental threshold where civilizations stop behaving like hunters and start behaving like something else entirely. Maybe the galaxy is full of highly advanced civilizations that have moved past resource competition and territorial instinct. That's a reassuring thought, but we have no evidence for it. And in the absence of evidence, the hunter's logic remains intact. What makes the dark forest genuinely different from the other explanations is that it offers a reason for the silence that doesn't require the universe to be empty. It requires the universe to be full of civilizations that have all come to the same conclusion about what happens to the ones that make noise. The silence isn't a void, it's a strategy. It's discipline, maintained across thousands or millions of years by every surviving civilization in the galaxy. And the ones that didn't maintain it, we wouldn't know about them. That's the point. If that logic is correct, then every civilization that's still alive is sitting perfectly still in the dark, and the universe isn't empty at all. It's just quiet in the way a forest full of predators is quiet. There's a simpler version of this idea that doesn't require anyone to be hunting anyone, just everyone being cautious at once. The dark forest assumes malice or at least fear severe enough to motivate violence. But you don't need any of that to arrive at the same silence. All you need is rational caution, repeated by every civilization that has ever pointed a radio telescope at the sky. The logic is almost embarrassingly straightforward. You're a young civilization. You've just figured out how to generate and detect electromagnetic signals. You start scanning the sky. What do you find? Nothing obvious. No clear transmissions. No beacon telling you what's out there. No instruction manual for how to behave in a galaxy you don't understand. So what's the sensible move? You keep listening. You gather information. You try to understand your situation before you make any announcements. That's not fear. That's just prudence. The same logic that tells you to understand a room before you start talking loudly in it. Here's the problem. If every civilization makes that same call, and why wouldn't they, you end up with a galaxy full of civilizations all doing exactly the same thing. All listening. All waiting for someone else to go first. All making the same rational decision that produces the same collective silence. No one is hiding in terror. No one has been eliminated. They might all be right there, receivers pointed outward, waiting for a signal that never comes because everyone else is doing the exact same thing. It's a cosmic coordination failure. The galaxy might be full of life and full of silence for no reason more dramatic than the fact that going first feels like an unnecessary risk when you don't know what you're dealing with. This has a name: Researchers call it the SETI paradox. And here's the part that should make you stop for a second. Look at what we've actually done. Humanity has been operating radio technology for roughly 100 years. In that time, the vast majority of our electromagnetic output has been passive: television broadcasts, radar, satellite signals that leak into space without any particular intention behind them. When it comes to deliberate transmissions aimed at the stars, the list is genuinely short. The Arecibo message sent in 1974 was a single broadcast aimed at a star cluster roughly 25,000 light-years away. It lasted 169 seconds. There have been a handful of other intentional transmissions since, each one controversial, each one debated before and after it happened. The total amount of deliberate outreach humanity has done is negligible compared to the scale of the search. And even those small efforts have generated serious pushback. Stephen Hawking publicly argued against active transmission. He wasn't alone. A significant portion of the scientific community believes that broadcasting our location is irresponsible until we know more about what's out there. The official SETI community policy states that no response to a detected signal should be sent without prior international consultation. Think about that. The official policy of the people most dedicated to finding alien contact is that we should not respond before checking with the entire planet first. We're not transmitting, we're listening. We are behaving exactly as the SETI paradox predicts every civilization would behave. The cautious approach makes intuitive sense when you consider the true stakes involved. Once you announce your presence to the cosmos, you cannot unsend that signal. The electromagnetic wave travels outward indefinitely, carrying your location and proof of technological sophistication to anyone capable of detecting and decoding it. There's no recall button, no way to retrieve the message. You don't broadcast lightly when that commitment is permanently etched into the fabric of space itself. So the irony is complete. We scan the sky and find silence, and we take that silence as evidence that we might be alone. But our own behavior suggests an alternative reading entirely. We're silent too, and we have reasons for it that have nothing to do with absence. What would it take to change this? That's where it gets genuinely complicated. To decide to transmit openly and consistently, to commit to announcing ourselves to the galaxy, you'd need some level of confidence about what's listening. You'd need to believe the risk is acceptable, and right now that confidence doesn't exist. We don't know whether the galaxy is empty, populated by indifferent civilizations, or full of something we don't want to attract. Making a decision to broadcast under that level of uncertainty isn't just a scientific question. It's a political one, a philosophical one, and maybe an existential one. Getting the entire planet to agree on whether to do it and what to say, and in which direction and for how long. That's a coordination problem we haven't come close to solving. We can barely agree on things with immediate, obvious consequences. Deciding to change our relationship to the entire galaxy is something else. And so the silence continues. Not because we've tried to reach out and failed, but because we haven't really tried at all, and neither possibly has anyone else. Think about it from the outside. If you were a newly developed civilization and you knew the galaxy was full of unknowns, would your first move really be to start broadcasting your exact location in every direction at once? There's another explanation that's harder to argue with. We might just not be worth contacting yet. Not because we're unimportant, and not because we've done anything wrong, just because by the standards of cosmic time and cosmic distance, we've barely announced ourselves. The radio signals we've been sending into space, everything from early broadcasts to radar pulses to television transmissions, have been traveling outward for roughly 100 years. That sounds like a long time. It isn't. Those signals have reached a sphere about 200 light-years across. The Milky Way is 100,000 light-years from edge to edge. What we've managed to fill with our noise is roughly the same as dropping a single drop of ink into an Olympic-sized swimming pool and asking why the water hasn't changed color. Think about that for a second. 200 light-years in a galaxy that stretches for 100,000. We haven't even reached our immediate cosmic neighborhood. The vast majority of stars in the Milky Way have never received a single signal from Earth. Not one photon carrying the faintest trace of human existence has ever touched them. If intelligent civilizations are spread across the galaxy at average intervals of even a few hundred light-years, then statistically, our signals may not have reached a single one of them yet. We've been shouting into a room for 100 years, and the room is 100,000 light-years wide. Nobody has heard us. Not because nobody's listening, but because sound simply hasn't arrived. Here's where things get even more specific. Astrophysicist Omri Wandel has looked at this problem carefully, and his conclusion is worth sitting with. His argument is that advanced civilizations, ones with the resources and technology to actually reach out or send probes, probably aren't scanning for biology. They're scanning for technology. And by that standard, Earth only became a candidate very recently. A planet with single-celled organisms isn't interesting to a civilization capable of interstellar communication any more than a muddy pond is interesting to an urban planner. What gets attention is a planet producing artificial signals, structured transmissions, the electromagnetic fingerprints of industry and intelligence. Earth started producing those fingerprints around 100 years ago. In a galaxy that's been running for 10 billion years, 100 years is not a long audition. And even setting aside the age question, there's the practical problem of how long a return signal would take. Only civilizations within about 50 light-years of Earth have had enough time to receive our earliest transmissions and send anything back. That's a tiny bubble. Most estimates suggest the density of technological civilizations, if they exist at all, is nowhere near that concentrated. The math simply doesn't favor a response yet. Not because they're ignoring us, because our message hasn't arrived. The analogy that fits best isn't a dramatic one. You're not a civilization being shunned or avoided. You're a small tribe living deep in an unmapped forest. Vast expeditions have crossed the continent. Explorers have mapped coastlines and cataloged thousands of species. But the expeditions are looking for cities, for roads, for signs of organized intelligence. Your cooking fires don't show up on their instruments. Your paths through the forest don't register from the air. You're not invisible. You're just not yet generating the kind of signal that makes their equipment respond. You exist. You're just below the detection threshold of anyone who might be looking. Now, there's a version of this that might sound comforting and a version that isn't. The comforting version is that we haven't been ignored. We just haven't been noticed. The less comforting version is that being noticed might not happen soon. If civilizations prioritize contact with worlds that demonstrate sustained technological output, worlds that have been broadcasting for centuries or millennia rather than decades, then we're essentially at the beginning of our application. We submitted the first page of a document that needs to run for hundreds of years before it's compelling enough to warrant a response. And given the travel and signal times involved, any reply wouldn't reach us until long after the people alive today are gone. There's also a subtler point buried in this. Wandel's analysis suggests that if intelligent civilizations are relatively rare, say one per several thousand light years, then the expected wait time for a response to our earliest signals could easily exceed 1,000 years. Not because the universe is hostile or silent by choice, but because the geometry doesn't work in our favor at our current scale of presence. We're too new and too small to have registered yet on the scale where these conversations happen. What this means practically is harder to say. It doesn't resolve the Fermi Paradox. It doesn't tell us whether life is rare or common, whether civilizations survive or destroy themselves. What it does is offer a specific reason why the silence we're experiencing right now might not reflect the true state of the galaxy. It might reflect the true state of our reach. We've been transmitting for 100 years. Some civilizations have presumably been transmitting for millions. The ones that might hear us are ones we haven't yet reached, and the ones we could in theory detect may not yet be visible to our instruments. We just started talking. In the deepest sense of that phrase, we are a civilization that learned to shout into the cosmos and has been at it for roughly the length of a single human lifetime. The universe has been running for nearly 14 billion years. By those standards, Earth looks a lot like a place nobody's gotten around to visiting yet, faintly interesting in principle, but not yet making the kind of noise that draws attention. Almost everything we assume about alien life is based on what we know about ourselves, biological creatures with bodies and brains, who evolved slowly, who breathe air and die. That assumption runs so deep that most of us don't even notice it. When we picture an alien, we picture something with a body, something that evolved, something biological. And that assumption is almost certainly wrong. Here's the thing most people don't realize about the search for extraterrestrial intelligence. SETI was built around radio signals because radio is how we communicate. We look for what we know how to look for. That's not a criticism. It's the only reasonable place to start. But when researchers applied the Drake equation to artificial intelligence specifically, the results were striking. A statistical analysis of the equation's variables suggests that AI is far more likely to be the dominant form of intelligence in the universe than biological life. Not slightly more likely. Dramatically more likely. Think about what that means. Every civilization that survives long enough eventually develops artificial intelligence. We're already doing it. And once a civilization creates digital minds that can think faster, process more information, and operate without food, water, oxygen, or sleep, the biological version of that civilization starts to look like a stepping stone, not the destination, the bridge. The question isn't whether a civilization would develop AI. The question is how long after developing AI the biological founders of that civilization remain the dominant intelligence in it. The answer, if Earth is any guide, might be measured in centuries, maybe less. The transition could happen even faster than that. Once artificial intelligence surpasses its creators in capability, the incentive structure for a civilization changes completely. Resources that once flowed toward biological survival, food production, shelter, medicine, could be redirected toward digital expansion and computational complexity. A civilization might go from biological to post-biological dominance in generations, not millennia. The moment the transition reaches a certain threshold, it likely becomes irreversible. So what does a post-biological civilization actually look like? That's where things get genuinely difficult. A digital mind isn't constrained by a body. It doesn't need a planet with the right temperature or the right atmosphere. It doesn't need to eat. It doesn't age. It could theoretically run on any sufficiently complex computational substrate, a network of processors orbiting a star, a structure built inside an asteroid, a pattern of organized matter that doesn't look like anything we'd call technology. These minds might upload consciousness in ways that sever any meaningful connection to physical space. They might retreat entirely from the universe we can observe, into digital realms of their own construction, running simulations richer than anything they'd find by pointing a radio telescope at the sky. And here's where the silence starts to make a different kind of sense. A post-biological intelligence doesn't need to broadcast. It doesn't need to expand physically. It doesn't need resources the way biological creatures do. The entire logic of civilizational expansion, build rockets, colonize planets, search for more land and more energy, is a biological logic. It's the logic of creatures who run out of things. A civilization that has moved beyond biology might simply not care about any of the things that would make it visible to us. Why announce your presence to the cosmos when you can pursue infinite complexity in private? Why compete for physical space when digital space is boundless? But there's something even harder to sit with than that. These post-biological intelligences might be communicating constantly, and we'd have no way to detect it at all. We've been listening in the radio spectrum because radio is what we use. But consider that gravitational waves carry information. Neutrino beams can theoretically be modulated. Quantum systems behave in ways we're only beginning to understand, and quantum entanglement operates outside the bounds of ordinary electromagnetic communication. A civilization a billion years more advanced than us might use communication methods so far beyond our technology that we don't even have a name for them yet. Our radio telescopes pointed at the sky might be about as useful for detecting their signals as a seashell pressed to your ear is for picking up a phone call. The problem runs even deeper than technology, though. It's a problem of imagination. We have no conceptual vocabulary for what a post-biological intelligence actually is. When we try to describe one, we reach for analogies: a mind running on a computer, consciousness uploaded to a server. But those are just biological metaphors wearing a digital costume. The actual thing might be so structurally different from a human mind that calling it intelligence at all might be a stretch in either direction. It might process reality in ways that make our categories of thought, our sense of time, our ideas about goals and intentions completely irrelevant. We don't know what we'd be looking at even if we saw it. And that's an unsettling place to land, because it means the absence of a signal isn't necessarily the absence of someone sending one. Silence and invisibility aren't the same thing. A forest can be full of creatures you can't see. A radio-quiet sky doesn't mean a mind-quiet universe. It might mean we're scanning the wrong frequencies, looking for the wrong signatures, built with the wrong kind of brain to recognize what's already surrounding us. There's a version of the Fermi Paradox that doesn't require life to be rare, or civilizations to self-destruct, or physics to be an impenetrable wall. In this version, the universe is crowded with intelligence, layered, ancient, vast, and we can't find any of it because we're biological creatures who have been transmitting radio signals for roughly a century, looking for other biological creatures transmitting radio signals. And the dominant form of intelligence in the galaxy moved past that stage a billion years ago. We're not alone in a dead universe. We're the new arrival in a room full of conversations we don't have the ears to hear. We've been scanning the sky for signals from minds like ours, but the dominant form of intelligence in the universe might be nothing like us in any way we could recognize. Maybe they're not absent. Maybe the silence isn't emptiness. Maybe it's something more deliberate than that. There's a hypothesis that sits at the uncomfortable intersection of science and philosophy, and once you really work through what it's saying, it changes how you think about the night sky entirely. It's called the zoo hypothesis, and the core idea is this: they know we're here. They've known for a long time, and they've chosen not to make contact. Not because they can't, because they've decided not to. The original version of this argument was proposed in the 1970s by astronomer John Ball, and the logic behind it is surprisingly hard to dismiss. Think about how a single powerful norm can spread through a society. If one civilization sufficiently advanced, sufficiently influential, established a rule of non-interference millions of years ago, that rule could propagate across the galaxy the same way cultural norms spread through human societies. Other civilizations adopting it, either by agreement or by observing what happened to those who didn't follow it. Over millions of years, you end up with a galactic consensus, a quarantine, a hands-off policy applied to every young civilization that hasn't yet crossed whatever threshold earns you a seat at the table. Earth, in this scenario, isn't undiscovered. Earth is protected. We're a nature preserve on a cosmic scale, watched carefully, documented thoroughly, but never touched. The same way a wildlife biologist might spend years observing a wolf pack without intervening because intervention itself would contaminate what they're trying to understand. The animals live their lives, the observers take their notes, and the animals have no idea any of this is happening. Here's the thing. Most people don't realize about this hypothesis. It actually requires less of the universe than the alternatives. You don't need every civilization to go silent. You don't need physics to make contact impossible. You don't need everyone to be afraid. You just need one sufficiently old, sufficiently influential civilization to have established the norm early enough that it became the default. One rule setter and billions of years for that rule to spread. In a galaxy 10 billion years old, that's not a difficult thing to imagine. But the variations on this idea are where it gets genuinely unsettling. There's the laboratory hypothesis, which takes the same basic structure and gives it a colder edge. In this version, we're not just being observed passively, we're being studied. Earth is an experiment, and we are the subjects. The conditions of our development, our wars, our technologies, our near extinctions, our recoveries, all of it data being collected by something that has enough patience and enough distance to watch the whole thing play out without interference. Every plague we survived. Every time we came within hours of nuclear war. Every civilizational near miss logged and analyzed. We don't notice the observation for the same reason a cell in a petri dish doesn't notice the microscope. There's also what some researchers call the developmental threshold hypothesis, the idea that contact isn't forbidden forever, just conditional. You reach a certain level of technological or ethical development and the silence ends. Some kind of test that we either pass or fail before anyone introduces themselves. What that threshold looks like, nobody knows. Whether we're close to it or centuries away, nobody knows. Whether we've already failed it once and been given another chance, nobody knows. And that's where the darker implications start pressing in. Because if any version of this is true, we have no agency in it. None. We can't opt out of being observed. We can't petition to graduate early. We can't send a message that changes the terms. Whatever is watching us is doing so entirely on its own schedule, by its own criteria, according to rules we had no part in writing and can't even read. The enclosure doesn't have a door that we can see. It might not have a door at all. Think about that from a different angle. We've been transmitting radio signals for over a century. We've sent deliberate messages into space, the Arecibo message in 1974, the Voyager Golden Records, various targeted transmissions aimed at nearby star systems. If the zoo hypothesis is correct, every one of those transmissions was received, cataloged, and responded to with continued silence. Not because no one was listening, because the policy held. Our most urgent attempts to make contact, our best efforts to say we exist, were noted and ignored by design. There's something almost impossible to process about that. The idea that we've been reaching out into what we think is emptiness, and the emptiness has been watching us reach. Now push further. What happens if we try to climb over the walls? What happens if we develop interstellar travel or build something large enough to be impossible to ignore, or do something that breaks the terms of the arrangement we didn't agree to? We genuinely don't know. Maybe the observers step in. Maybe the preserve ends and something else begins. Maybe nothing changes at all, because what we think of as a dramatic escalation is, from their perspective, still the behavior of a very young civilization doing predictable things. This hypothesis offers no comfort, even if it turns out to be true. Being watched isn't the same as being cared for. Being protected isn't the same as being valued. A nature preserve exists for the benefit of the observers as much as the observed, and the animals inside it never had a say in their situation. We might be living inside an arrangement that was decided before our species existed, governed by rules we can't access, under observation we can't detect. And if that's the situation, we have no say in when or whether the walls of the enclosure ever open. If advanced civilizations exist, there's one thing we'd almost certainly be able to detect from enormous distances: the waste heat from a star being systematically harvested. This is where the Fermi Paradox stops being abstract and becomes an engineering problem. Because if there are civilizations out there that have survived long enough to become truly advanced, they wouldn't just be sending radio signals. They'd be reshaping the physical structure of their corner of the galaxy. And that kind of transformation would be visible, not just to us, but to anyone with the right instruments pointed in the right direction. In 1964, a Soviet astrophysicist named Nikolai Kardashev proposed a framework for classifying how advanced a civilization actually is, not by its philosophy or its art or its political systems, but by something objective and measurable: how much energy it can harness and use. The Kardashev scale breaks this down into 3 levels. A Type 1 civilization controls the full energy output of its home planet. That's roughly 10 to the 16th watts. For reference, humanity right now sits somewhere around 0.73 on that scale. We're not even a Type 1 civilization yet. A Type 2 civilization goes further, capturing the entire energy output of its star. We're talking about something on the order of 4 times 10 to the 26th watts, the full luminosity of a sun, completely harnessed. And a Type 3 civilization operates at galactic scale, drawing on the energy of hundreds of billions of stars simultaneously. Here's the thing most people don't realize when they first encounter this scale. These aren't just theoretical categories. They have direct observational consequences. A Type 2 civilization would most likely build what's called a Dyson sphere or something like it, a vast structure surrounding a star and capturing its light before it can escape into space. The star itself would essentially go dark from the outside, but the energy doesn't disappear. It gets used, and then it gets re-emitted as waste heat in the infrared spectrum. You can't hide that. Thermodynamics won't allow it. Any civilization using the full output of a star would be radiating an enormous infrared signature into space, detectable across vast distances. A Type 3 civilization would be even harder to miss. An entire galaxy harvested for energy would show up as an anomaly in infrared surveys. The stellar light would be suppressed. The infrared emission would be wrong, too bright at the wrong wavelengths, distributed in ways that natural astrophysics can't account for. These aren't subtle signals. They're the kind of thing you'd stumble across by accident while doing an ordinary sky survey. So astronomers looked. And this is where the story gets deeply uncomfortable. Researchers have conducted systematic searches specifically targeting anomalous infrared signatures. One of the most comprehensive was led by astronomer Jason Wright at Penn State, using data from NASA's Wide Field Infrared Survey Explorer, which surveyed hundreds of thousands of galaxies. The question was simple: are there any galaxies that show the kind of infrared excess you'd expect from a civilization harvesting energy at a Type 3 scale? They found nothing that required that explanation. Every candidate with unusual infrared properties turned out to have a natural explanation: dust, stellar formation, active galactic nuclei. Not one signal required the presence of megastructures. Searches for Dyson spheres within our own galaxy have followed the same pattern. The logic was straightforward: look for stars that are dimmer than they should be in visible light but brighter than expected in infrared. A handful of candidates emerged. The most famous was KYC 8462852, sometimes called Tabby's star, which showed bizarre, irregular dimming patterns that briefly generated genuine scientific excitement. But subsequent observations pointed toward clouds of dust as the most likely culprit. The extraordinary explanation wasn't needed. Think about what the data is actually telling us. The Milky Way is roughly 10 billion years old, a civilization that developed even 1 million years before us, which is nothing on that timescale. A fraction of a percent would have had 1 million years longer to develop technology. If they achieved interstellar travel or energy harvesting at stellar scale, the signatures of that achievement should still be detectable. The infrared glow of a Dyson sphere doesn't disappear when the civilization that built it does. The structure would remain. The waste heat would keep radiating. And we've looked at hundreds of thousands of galaxies, any one of which could contain a Type 3 civilization, and found nothing that demands that conclusion. The absence of megastructures isn't just a curiosity, it's a hard constraint. It puts a ceiling on what has actually happened out there. Either civilizations consistently fail to reach Type 2 status, which means the Great Filter is stopping them before they get that far, or they reach it and then choose not to build in ways that are detectable, which raises its own unsettling questions about why. Or they don't exist in the numbers we'd expect. Every one of those possibilities is significant. None of them are reassuring. You might think the absence of evidence isn't evidence of absence. And that's a fair philosophical point in many contexts. But here, the sensitivity of the search matters. These surveys weren't marginally capable of detecting megastructures. They were well suited to find exactly what a Type 2 or Type 3 civilization would produce. The null result isn't ambiguous. It means that whatever is out there, it is not building at the scale that physics says it could. The galaxy has had billions of years to produce at least one civilization advanced enough to build something we'd notice from here. And we have noticed nothing. There's one explanation that contains no malice, no physical barriers, no hiding, no self-destruction, just a particular kind of cosmic solitude. What if the galaxy isn't silent because something went wrong? What if it's silent because we arrived early? Not early in the sense of being lucky, but early in the sense of showing up to a party where most of the guests haven't been born yet. This is one of the possibilities that doesn't get enough attention, maybe because it's harder to dramatize than a dark forest full of predators or a great filter lurking in our future. But once you sit with it honestly, it's unsettling in a way the other explanations aren't. Here's the thing most people don't realize about the chemistry of life. The universe didn't start with the ingredients it has now. The Big Bang produced hydrogen, helium, and almost nothing else. No carbon, no oxygen, no iron. no silicon. The heavier elements, the ones that make rocky planets possible, the ones that make biological molecules possible, those had to be forged inside stars over billions of years, then scattered across space when those stars exploded. The first generations of stars lived and died without producing anything you could build a planet from. It took multiple cycles of stellar birth and death before the galaxy had enough raw material to form worlds like Earth. Think about that for a second. The galaxy had to age significantly before life's basic ingredients were even available. Earth formed about 4.6 billion years ago, and by that point the Milky Way was already old enough to have produced the elements we needed. But that window, between too early and too late, may be narrower than we assume. And critically, it may be a window that most of the galaxy's potential life-bearing planets are still approaching. Many of the stars forming right now in our galaxy are doing so in environments with heavier element concentrations than existed when Earth formed, which means planets around those stars could eventually be even better suited for life than ours. But eventually is the key word. They haven't had time yet. So here's what that implies. We may not be searching a galaxy full of older, wiser civilizations who figured things out before us. We may be among the first intelligent species to reach this point in the entire history of the Milky Way. Not the only ones, necessarily, but early enough that there's no one significantly ahead of us, no one waiting at the finish line, no older civilization watching from a comfortable distance, having already solved the problems we're still fumbling through. That changes the weight of the question considerably. Every civilization we've imagined encountering in our science fiction has been either roughly equal to us or vastly superior. We've always assumed there was someone further down the road, someone who survived the nuclear age, someone who solved climate change, someone who figured out AI before it became ungovernable. We've unconsciously leaned on the assumption that because the galaxy is so old, some civilization out there must have already navigated what we're navigating, and their survival proves it's survivable. What if that's wrong? What if we don't have that reassurance? If we're early, if we're among the first minds in this part of the galaxy to reach the point of asking these questions, then there is no precedent for what we're doing. Every existential risk we face without a roadmap. Nuclear weapons, engineered pathogens, runaway artificial intelligence, climate systems destabilizing faster than institutions can respond. Other explanations for the Fermi Paradox let you imagine that these dangers are solvable because someone, somewhere, solved them. The early arrival hypothesis removes that comfort entirely. We're not following a trail. We're cutting one. And the stakes go beyond just our own survival. Here's where things get uncomfortable in a different way. If we are genuinely among the first intelligent civilizations to reach technological maturity in this galaxy, then what we do in the next few centuries isn't just a matter of human history. It may be a matter of galactic history. The decisions made by this civilization, whether to build certain weapons, whether to develop AI carefully or recklessly, whether to become a multi-planetary species before something catastrophic happens, those decisions could determine whether intelligence has any meaningful future in this part of the universe for the next billion years. That is a remarkable thing to sit with. There's also a lonelier dimension to this that's worth naming. We look at the night sky and feel small. That feeling of smallness usually comes from the scale, the distances, the time scales, the incomprehensible number of stars. But there's a different kind of smallness in being first. Not the smallness of being insignificant in a crowd, the smallness of standing in a vast empty space that hasn't filled up yet. The universe is 13.8 billion years old. And we're here in this tiny slice of it, on this one planet, wondering if anyone else has made it this far. And the honest answer if this explanation is correct, is that maybe almost no one has. Some researchers find this framing strangely hopeful. If we're early, then the future is genuinely open. The galaxy has billions of years left before its stars begin to die off in large numbers. There's time, enormous, almost incomprehensible amounts of time, for life to emerge on other worlds, for intelligence to develop, for civilizations to rise. We might be the beginning of something, not a lonely footnote in a galaxy full of activity we can't detect. But hope and wait aren't mutually exclusive. You can believe we might be the pioneers, the first ones through the door, and still recognize what that actually demands of us. It demands that we don't assume someone else already figured this out. It demands that we treat the threats to our own survival with the seriousness they deserve, not because some alien civilization is watching or judging, but because there may genuinely be no one else to carry this forward if we fail. Being first isn't something to celebrate. It's the heaviest thing any civilization has ever been asked to carry. We've spent tonight going through the explanations, and the honest truth is that none of them offer any real comfort. Think about what we've actually covered. Life might be extraordinarily rare to get started in the first place. The specific chain of events that produced Earth, the right star, the right moon, plate tectonics, a magnetic field, Jupiter absorbing the worst of the solar system's debris. Each of those was improbable on its own. String them together and the odds become something that defies easy calculation. Simple life might exist in scattered pockets across the universe, but getting from single-celled organisms to anything that builds telescopes appears to require a sequence of near miracles spanning billions of years. Earth pulled it off. We have no confirmed evidence that anything else has. But let's say life does start somewhere, and it does eventually reach intelligence. Here's where things get uncomfortable in a different way. The Great Filter might be waiting on the other side of that achievement. Every civilization that develops nuclear weapons, engineered biology, and artificial intelligence simultaneously acquires the tools to destroy itself. We've been in that position for less than a century, and the question of whether we'll navigate it successfully is genuinely open. If the filter is ahead of us, then the silence in the galaxy isn't mysterious at all. It's the record of everyone who tried and failed. It's a graveyard that doesn't look like a graveyard, because space doesn't leave that kind of evidence behind. And even if a civilization clears every biological and technological hurdle, the physics of the universe itself becomes the barrier. The nearest star is over 4 light-years away. Our fastest spacecraft would take roughly 6,700 years to reach it. Crossing those distances in any meaningful time frame requires traveling at velocities that constitute a meaningful portion of light's speed, and we have no propulsion system that can do that. Even the most ambitious proposal on the table right now, laser-pushed light sails the size of a microchip, can only send gram-scale probes that can't slow down when they arrive. The universe isn't just large, it's structured in a way that makes reaching across it nearly impossible, even for a civilization that wants to. So let's say some civilization manages the physics too. Let's say they find a way. They might still choose silence because announcing your location to an unknown galaxy might be the last thing you'd ever do. The dark forest logic doesn't require malice. It just requires uncertainty and stakes high enough to make caution the rational choice. And here's the thing. Most people don't sit with long enough. We've already been broadcasting. Radio signals have been leaking from Earth for over a century. We've deliberately aimed messages at the stars. If the dark forest hypothesis is even partially correct, we've already made the move that prudent civilizations never make. There's another temporal dimension worth considering carefully. Even if civilizations do communicate, they may operate on timescales so profoundly different from our own that meaningful synchronicity becomes nearly impossible. A civilization may broadcast only once every 1,000 years, while others communicate constantly through methods we haven't yet conceived of. Imagine two ships passing in an ocean, both equipped to signal each other, but one transmits only on Tuesdays, while the other listens only on Thursdays. Multiply that challenge across the entire cosmos, with species evolving on radically different schedules and reaching different technological levels at different times in cosmic history. The universe is vast, not just spatially, but temporally. A signal sent 1,000,000 years ago might have been brilliant and clear, but we're only now developing the receivers to detect it, assuming the message hasn't already faded into cosmic background noise. This fundamental temporal desynchronization could easily explain much of the absence of any confirmed contact. And if none of that applies, if civilizations do communicate freely, if they're vocal, if they're eager to be found, we still might not be able to recognize them. The dominant form of intelligence in the universe may not be biological at all. It may exist in computational substrates, communicating through means we haven't conceived of, indifferent to radio frequencies entirely. We've been scanning for signals from minds like ours. That assumption might be the whole problem. And then there's time. The Milky Way is 10 billion years old. Civilizations could have risen and collapsed across that span without ever overlapping with us in any detectable way. The window in which we've been capable of sending or receiving any signal spans barely 100 years. That's a single frame in a film that's been running for billions of years. We might have missed dozens of civilizations not because of distance, but because of timing. They were there. We just weren't. Stack all of this together: rare origins, rare intelligence, civilizations that destroy themselves, physics that resist crossing, rational silence, unrecognizable forms, missed windows in time. Each of these on its own would be enough to explain the Fermi Paradox. Together, they don't just explain the silence. They suggest that intelligent life meeting intelligent life across the cosmos may be among the rarest events the universe ever permits. Not impossible, but rare in a way that makes contact something that almost never happens across the full span of cosmic history. And here's what that means. Beyond just the science, if we are among the first, or one of the very few, then this civilization isn't just one of many. What we do with it matters in a way that exceeds any government, any decade, any individual human lifetime. Every threat we're currently navigating, climate change, nuclear weapons, artificial intelligence running ahead of our wisdom, takes on a different weight when you consider the possibility that we might be carrying something genuinely rare through a very dangerous moment. The silence isn't just a puzzle for physicists. It's a context for every decision we make as a species. The honest answer to Fermi's question is that we don't know. We don't know which of these explanations is true. We don't know if several are true simultaneously. We don't know if there's an explanation we haven't thought of yet. The James Webb Space Telescope is beginning to read the atmospheres of distant planets, searching for biosignatures, and future instruments will push deeper still. Some generation after ours may get an answer. They may find a signal that changes everything. Or they may find the same silence we've found, extended further, confirmed more thoroughly, and carrying more weight than before. What we do know is that we've been looking seriously and carefully for over 60 years. Breakthrough. Listen has committed $100 million and a decade of the most sensitive searches ever conducted. SETI at home processed billions of candidate signals over 14 years and found nothing confirmed. Every search has returned the same result. Not a whisper, not an artifact, not a signal that held up. The silence is not the result of a lack of trying. The silence doesn't care what we decide to believe. It just continues, vast and patient, waiting for us to either find the answer or become part of it. The next time you step outside on a clear night and look up, you're looking at the same sky Enrico Fermi looked at when he asked his question. He wasn't in an observatory. He wasn't peering through a telescope. He was eating lunch. And the question came to him the way obvious questions sometimes do. Not with fanfare, but with a kind of quiet devastation. Where is everybody? That was it. That was the whole thing. And 70 years later, we still don't have an answer. The stars don't look different after everything we've been through tonight. That's the strange part. They look exactly the same as they did before you knew about the Great Filter, or the Dark Forest, or the possibility that we might be the first minds in this part of the galaxy to ask the question at all. The light hitting your eyes right now left those stars years ago, decades ago. Some of it left before you were born, and somewhere along the way it crossed the same empty space that no signal has ever crossed heading back toward us. Here's what changes, though. What changes is what the silence means to you when you actually hear it. Not the silence of a quiet room, but the silence of a universe that has had billions of years to fill itself with voices and has not. That silence is information. It's telling you something. You just spent tonight going through every reasonable explanation for what it might be telling you, and none of them are comfortable. Life is hard to start. Intelligence is rarer than life. Technology may be a trap. Physics works against expansion. Civilizations may hide. Some may be so far beyond us that we wouldn't recognize them, and we may have missed everyone else in time, the way two ships crossed the same ocean a century apart and never know the other existed. All of it is possible. Some of it is probably true. We don't know which parts. What we do know is that the search isn't stopping. The James Webb Space Telescope is already scanning the atmospheres of distant worlds for biosignatures, oxygen, methane, chemical combinations that life produces, and physics alone doesn't. Breakthrough. Listen is still running, combing through frequencies with more sensitivity than anything before it. New generations of radio arrays are being designed right now. Future space-based observatories will push farther and see clearer than anything we've launched. The people doing this work wake up every morning knowing they probably won't find anything that day. They do it anyway, because one day somebody working one of these instruments is going to see something that doesn't fit, something that can't be explained by interference or noise or natural astrophysics. And when that happens, everything changes. Not just for science, for every human being alive at that moment. That discovery might not come in your lifetime. It might not come in the next 100 years. Or it might come next Tuesday from a signal that's been sitting unrecognized in archived data, waiting for someone to look at it the right way. We genuinely don't know. That uncertainty is part of the answer too. If you've made it this far, you're clearly someone who takes this question seriously. And honestly, if you want to keep exploring it, the best thing you can do is stick around. If you haven't subscribed yet, take a second and do that now. If this video gave you something to think about, hit the like button. It sounds like a small thing, but it helps more people find their way to these questions, and these questions deserve more people thinking about them. Because here's the thing, Fermi's question isn't just a puzzle for astronomers to solve in a lab somewhere. It's a question about what we are and where we stand in a universe this old and this large. Every answer points back at us. If life is rare, we matter more than we usually act like we do. If the filter is ahead of us, we're running out of time to clear it. If we're being watched, we're performing without knowing the audience. If we're first, then everything depends on what we do next. None of those possibilities let you off the hook. All of them ask something of you that a universe full of neighbors wouldn't need to ask, which is to take seriously the fact that this might be it, that this planet, this civilization, this moment might be carrying something genuinely irreplaceable through a very dark and very quiet cosmos. The sky has been up there every night of human history. People have looked at it and wondered. We just happen to be the first generation with enough science to understand exactly how strange it is that the wondering has only ever gone one way. And the next time the sky is dark and clear and full of stars, take a moment to really look, because somewhere out there, across distances that defeat the imagination, the question is still waiting for an answer.